In this video, I'm going to talk about my project, CheckMySteps, a web app to help students fix their algebraic mistakes. To start off, let's talk about two categories of math mistakes. There's self-correctable mistakes and there's non-self-correctable mistakes. Self-correctable mistakes are those that a student can correct with minimal help. For example, in response to a self-correctable mistake, a student might say, "Duh, I forgot about the negative sign." Or, "Oh yeah, I learned that before, but I didn't think about it until you mentioned it." Essentially, the student has already learned about the mistake, but just needs a stimulus to help them remember the mistake or notice that they've absent-mindedly made the mistake. On the other hand, with non-self-correctable mistakes, the student needs a thorough explanation. You might hear the student say, "I don't understand why this is wrong," or "I'm not quite getting it. Can you explain it in a different way?" Non-self-correctable mistakes require a teacher to create a human explanation for the student that is tailored to the student's background, interests, and general frame of mind. On the other hand, with self-correctable mistakes, the teacher processes student work like a computer, parsing through the lines of student work and tagging any mistakes for the student to review. This isn't very enjoyable for the teachers, and it's not a great use of their time either. So why don't we try to automate it? That's precisely what my web app, CheckMySteps, attempts to accomplish. First, students enter their steps in their work line by line. Then they submit their work and each line is checked against the previous line. If a mistake is detected in any step, then a counterexample is displayed, and any potential mistakes are listed for the student to review. Each potential mistake classifies the student's error as a potential violation of some algebraic rule and informs the student of the correct interpretation of that rule. Now let's talk about how the web app works. CheckMySteps is deployed on Heroku as a Flask application. The front end of CheckMySteps leverages an array of MathQuill math fields to receive input from the user. The user is able to type math symbols using LaTeX or other intuitive key combinations, such as the less than key followed by the equals key to make the symbol less than or equal. The step checking module leverages SymPy to check each line against the previous line and generate a counterexample in the event of any mistake. SymPy is also used in the mistake classification module, which uses the content of the lines preceding and following the mistake to classify the mistake. Now let's take a deeper dive into the step checking and mistake classification modules. Let's first go through an example of step checking for expression input. Say we begin with a step where the line before the step is the quantity x plus 3 squared, and the line after the step is x squared plus 6x plus 9. We already know that step is correct because that's what we get when we multiply out the binomials using the foiling method. But let's see how CheckMySteps verifies this. CheckMySteps starts by constructing a difference expression, consisting of the expression following the step minus the expression preceding the step. It then simplifies that difference expression, and in this case we see that simplifies to 0. Then the step is deemed correct if the difference expression simplifies to 0, because that just means that the expression following the step is equal to the expression preceding the step. Okay, let's try another step. This time the quantity x plus 3 squared turns into x squared plus 9 after the step. Now we know this is wrong because the student clearly hasn't foiled the expression. The student just distributed that squared exponent to the x and the 3, which isn't correct. There should be a plus 6x term in the middle when you multiply it out. Again, CheckMySteps computes the difference expression, but this time the difference expression simplifies to negative 6x squared. Since it doesn't simplify to 0, the step is then labeled as incorrect. Lastly, a counterexample is chosen. We try to start off with the easiest possible counterexample, say x equals 0, and check whether that makes the expression preceding the step and the expression following the step evaluate to different amounts. In this case, 0 doesn't work as a counterexample because both expressions just evaluate to 9. So then we continue down the line of other possible counterexamples, next going to 1, and then if 1 doesn't work, going to 2, so on to 9, then to -1 to -2, so on and so forth, until we get to -99. Usually we won't have to travel that far. For example, in this case, x equals 1 provides a good counterexample. The expression preceding the step evaluates to 16, and the expression following the step evaluates to 10. Now let's run through an example of step checking for equations. So we'll start off with a step x squared minus 1 is equal to negative of the quantity 1 minus x, and that equation turns into x squared minus 1 equals -1 plus x. We already know that this is a valid step. The student has just distributed the negative sign on the right-hand side to the two terms inside of the parentheses. So how does CheckMySteps verify this? Well, it starts by computing the solution sets of each equation. So the first equation has a solution set of 0, 1, and the second equation also has a solution set of 0, 1. Then it determines that the step is correct if the solution sets are exactly the same, like they are here. Now let's take a look at a different step, starting off with the same equation, but this time the student forgets to distribute the negative sign to the x on the right-hand side. So instead of plus x like we should have, we have minus x. When CheckMySteps computes the solution sets, it finds that the solution set of the first equation is still 0, 1, but the solution set of the second equation is now 0, negative 1. And since these solution sets are not exactly the same, it labels the step as incorrect. Lastly, a counterexample is chosen from the symmetric difference of the solution sets, which just consists of those solutions which are not common to both sets. In other words, the solutions that only appear in one of the sets. Here, the solution of 0 is common to both sets, so we don't include that in counterexamples, but we do choose 1 or negative 1, because each of these solutions only appears in one of the sets. And to keep things simple, we only choose one of those candidates for counterexample. We usually choose the smallest magnitude counterexample, with positive counterexamples winning any ties. So here we choose the counterexample of x equals 1 to show to the student. Moving on, let's talk about mistake classification. The mistake classification rules are called whenever a mistake occurs, and they use the content of the lines preceding and following the mistake. For example, one of the mistake classes is positive or negative root, and the feedback that is given to the student for this mistake class is that they're told that if x squared equals a, then x equals positive or negative root of a. So this would be meant to help a student who has forgotten to list the positive or negative root in a squared equation. Now the detection rule for this mistake class is that the previous line is an equation which contains an exponent, and a non-zero current solution is the negative of a previous solution. So let's demonstrate this detection rule on an example. The step consists of the equation x squared equals 3 turning into the equation x equals root 3. So first of all, we know that there is a mistake because the solution sets don't match up. The first equation has solution set root 3, negative root 3, and the second equation only has a solution set of root 3. So now that we know that there is a mistake, the detection rule is applied. The first part of the detection rule, previous line, is an equation which contains an exponent. We see that matches up here because the first line here is an equation and it has an x squared in it. Squared 2 is the exponent. The second part of the detection rule is that a non-zero current solution has to be the negative of a previous solution. And we indeed see this in our solution sets. There is a current solution of root 3 in the second equation, and that is a negative of negative root 3, which is a previous solution to the first equation. Now let's talk about how CheckMySteps was validated. The simplest method of validation was just to manually generate examples for each mistake class and then test each mistake class on those manually generated examples. But to minimize designer's bias, CheckMySteps was also tested on a sample of algebraic errors generated by a tutor who was unfamiliar with CheckMySteps. This sample of algebraic errors was based on the tutor's experiences with real-life students, and CheckMySteps detected a relevant mistake class for 10 of the 14 errors. Lastly, let's talk about some future work that can be done with CheckMySteps. First of all, one way to improve CheckMySteps is to implement more granular mistake classes. For example, the negative sign mistake class could be separated into dropped a negative sign and added an unnecessary negative sign. Another way to improve CheckMySteps would be to include location-specific mistake feedback. In other words, to highlight specific terms where the mistake occurred, so the student knows exactly where to look within their step to identify and correct the mistake. Lastly, CheckMySteps should be made to better handle equations which can't be solved using standard algebraic techniques.